Welcome to the Extreme Broadband Engineering Cable 101 training series. In this session, we'll cover passive troubleshooting. There are many electrical and mechanical aspects to passive devices. In this video, we'll look at how to troubleshoot them, not just cut them out, throw them away, and go. The things we'll cover in this video are how to troubleshoot insertion loss, port-to-port isolation, return loss, digital contacts, and second harmonics. The first thing we'll look at is insertion loss. Insertion loss is the attenuation the passive device has to the signal as it passes through it. Here we have a two-way splitter, and we're going to check it for proper insertion loss. Prior to any testing, always make sure that your test leads and connectors are in good condition. The average use of these is over 100 times a week, and it's a good practice to change them weekly. First, we'll check to see how much signal we have coming into the input. With the signal level meter, we're going to select channel 2, and we have 10 dBmV. Next, we'll check the output. Since the two-way has 3.5 dB of insertion loss, we'd expect a signal of 6.5 dBmV. If we measure something less than this, we could suspect that the splitter may be faulty. When looking at the specifications of passive devices, the tolerance is normally plus or minus 1 dB, so a 1 dB variance would be normal. If we're testing a three-way, we'd expect a loss of 3.5 dB on one port and 7 dB on the other two. A four-way would expect 7 dB per port, and an 8-way 11 dB. Insertion loss is considered a flat loss, where the loss at any frequency across the rated range of 5 to 1002 MHz is about the same. This measures several channels from the low to the high end of the frequency band. Here we'll use 5, 40, 55, 550, and 1000 MHz. Each channel measures 10 dBmV. Next, we'll measure the output. Now each frequency is measuring 6.5 dBmV for a loss at each frequency of 3.5 dB. So at each frequency, we have approximately the same loss. To illustrate this, we'll look at a frequency sweep on a network analyzer from 5 to 1002 MHz. You'll see that the sweep is fairly flat and varies slightly over the entire frequency band. The normal variance is a few tenths of a dB to 1 dB. With insertion loss, the loss is the same if it's going from the input to the output ports or from the output ports to the input. Here we're injecting 10 dBmV into the input at channel 78. On the output, we measure 6.5 dBmV for a loss of 3.5 dB. Now at 20 MHz, we're injecting 10 dBmV into one of the output ports. On the input, we measure 6.5 dBmV for a loss of 3.5 dB. So with passive devices, expect the same amount of loss in the downstream or the upstream. Next, we'll look at port-to-port isolation. Port-to-port isolation is the amount of signal separation that a device has between any two output ports. This helps to prevent interference to other services from high-level return signals. Here we're measuring a return signal of 55 dBmV at 24 MHz coming into one of the output ports. Next, we'll measure the amount of signal that is present on the other output port. In this example, we're measuring 25 dBmV, so the port-to-port isolation is 30 dB. With port-to-port isolation, a problem that you may see in the field is that someone connected the input to the output port in error. This would cause low signal on all outputs, and the one that's connected to the input is good. In this example, the input is connected to the output port. One outlet has good signal level, as this one's connected to the input port of the splitter, and the signal will flow from the output to the input with normal insertion loss of the splitter. The other outlets have poor signal level due to the port-to-port isolation of the splitter. Once the input cable is connected to the input port, all outlets will receive the proper signal. Next, we'll look at return loss. Return loss is the amount of signal that is reflected back towards the signal source by a device due to an impedance mismatch. With passive devices, one of the main causes of return loss is unterminated ports. Here we're looking at a network analyzer return loss sweep from 5 to 1002 MHz on the input port, with the output ports terminated. With proper termination, the return loss is at least 20 dB down, and at most frequencies way below that. This is a good return loss sweep. Now by removing the terminator from one port, we see a drastic change for the worse to the return loss. Now the return loss is in the 6 to 8 dB range. By unterminating one port, the return loss got worse by at least 12 dB. A good engineering practice is to terminate all unused ports when possible. Let's look at some of the signal impairments that return loss can cause. With analog video signal, you'll notice ghosting around images. With digital video, you can see freezing or tiling of the picture. And with data, you may experience slow data rates. Now let's look at the digital contacts. How you install a connector to the passive devices needs to be considered. If you take the easy way and twist the device onto the connector, you could scrape the plating from the digital contact and the center conductor and create a possible point for common path distortion to develop. With a properly made connector, it's advised to twist the connector onto the passive port. Contact plating material and the copper center conductor are compatible materials. Any change due to the scraping of the center conductor or contact plating can cause corrosion. This could be caused by the twisting of the passive device onto the connector as we showed earlier, or improperly prepared center conductors that can cause damage as they're inserted into the contact. Common path distortion can develop at any point where the forward and return signals are present, and there's a contact point, such as between a center conductor and a passive port contact. Normally this point of contact won't create common path distortion, but if the platings are scraped to the base metals, corrosion could develop due to dissimilar metals, causing a diode, and the forward signals get imposed on the return. Here's a spectrum analyzer sweep of the return band showing the common path distortion. It's identified by the peaks at 6 MHz spacing. This corrosion is very fragile, and if you remove the center conductor, the common path distortion will disappear, but be assured, it will return as the corrosion builds back up. Next, we'll look at second harmonic distortion. High-level modem transmissions in the reverse band traveling through saturated ferrite core material create second harmonic distortion interference in the forward band. Here we have a cable modem that is putting out 55 dBmV at 31 MHz. It's connected to the output of a splitter that has low-quality ferrite material. This material can become magnetized due to power surges or power ground loops. As the high modem signal passes through the ferrite material, it creates high second harmonic distortions, in this case at 62 MHz, twice the frequency of the modem's frequency. In an analog picture, this would look like pulsating noise, or digital video, freezing and tiling. By replacing the splitter with one that has high quality ferrite material, the second harmonics are low and do not cause any service issues. In the Extreme Broadband passive devices, we use a highly complex ceramic core material blended to suppress these interfering signals and improves the second harmonic distortion. In this video, we looked at how to troubleshoot insertion loss and how it's a flat loss, and the same in the downstream and the upstream. We looked at port-to-port isolation, return loss and the importance of termination, digital contacts and common path distortion, and finally second harmonics and the importance of using passives with high-quality ferrite materials. Thank you for viewing this training on passive troubleshooting. For additional training topics, see our website at www.extreme-broadband.com.